So hello guys, today is 31st of October 2021 and this is today's Leetcode challenge. The title of the question is flatten a multi-level doubly linked list. So let's go through the question. So let me read the question and then I will explain to you and then we will go through the solution. This is how usually the thing work here. So you are given a doubly linked list which in addition to the next and previous pointers, it could have a child pointer which may or may not be pointing to separate doubly linked list. These child lists may be one or more children of their own, so on. To produce a multi-level data structure as shown in the example below. This is the example they are referring to. So what we have to do, flatten a list so that all the nodes appears in the single doubly linked list. You are given the head of the first level of the list. So let me explain you this. So we will be given this kind of data structure. So we know doubly linked list, there is a node and node contains two pointer, one next pointer and one previous pointer. Next pointer points to the next node and the previous pointer points to previous node and a field for data. But this is a modified doubly linked list in which a node might contain next it is modified doubly linked list which might contain next, previous and as well as child field which will may point to a separate doubly linked list, and this child node may itself point to next level. So you can see there might be multiple levels of linked list, doubly linked list. So you can see this first level, this second level, and if you extend this and you can see that you can go further down and down. So uh, so what we have to do, we have to convert this into a single doubly linked list. So let's see how can we do that. Before going to you can see for that, for this particular question, let's see what is the resultant. So you can see 1 2 3 7 8 9 10 11 12 19 sorry 9 10 4 5 6. So 1 2 3 1 2 3 and you can see 7 8 9 11 12 7 oh sorry 7 8 9 10. Basically what we have to do, we have to merge this particular part between these two nodes. So similarly you can see for this particular linked list we will have to add this list to in between this list, and then the resultant list we will be adding into this. So you can see there is a relation like a recurrence. You can see if we apply the some logic on that, we can see similarly apply a logic on this also and similar logic to on this also. So one idea might be clear to you that we will be using recursion here. So let's see the solution. These are some of the extra test cases, and these are for the clearance on the question that if a question is like 1 2 null and 3 and null, so basically means first level contains 1 2 and null, and then second level contains 3 and null. Further clearance of this question is given here. You can see this list if you see here given 1 2 null and 3 4 null. So here representation is given as 1 2 null and 3. So but here you can see if it is written like this. So similar, if we apply similar logic as we have used here also, so 1 will be linked to 7. That will be wrong because 3 is linked to 7. So to fill these gaps we will be using null. See here we'll be using null and 7 8 9 and then null always there will be always a null at the end of the linked list, and to fill the void like these voids, and this will always be starting of the parent list. Like if you consider this as a child and parent, then the null will be always start with the parent. If the you might the here in this case null will not be here in this for these two, but it will be from here for this list, this from here. So this is all the we will be given as an input, but we have nothing to do with the input. It's just to understand that if you want to write your custom test case to test the algorithm, then you can write in this way. So these are the constraints. The number of nodes will not exceed 1000, and the value of the value in the node will be not be greater than 10 raised to power 5. So yeah, these are the. So I will appreciate, like I will like to I will suggest you all to try this problem on your own. I will drop the link to this problem in the description. You can go through the question, and you will see. I will see you after some time. So I hope you all tried this problem. Now let me take you to the solution. So this is my solution which passed all the test cases. Let's go through here. Yeah, so this is the my solution. You can see this is the problem. This function will be given to you, empty function. So I'm using recursion here. So what will be my logic? Let's go through the test case. So this is our given problem. So if it's like we will start from the like top level, and we will go through all the node. If a particular node contains a child, like this contains, so we will then call a recursive call on this function to check whether these, like all the child, similar logic on this, like we'll go through all the nodes and we'll check whether this contains loop or not. Yeah, so we were discussing the logic for this problem. So what we will do, we will go through all the nodes from, like consider this as a linked list. We'll go through all the nodes, and if a particular node calls like have a child, so we will then make the similar recursive call on this linked list, and then as this also contains a child, so we will call upon this. There will be at least one linked list that will not contain, otherwise we will have to add endless. We will not be able to solve this problem. There will be at least one list that will contain no children, so from that list we will start merging these. So what do we basically needs to merge, and we will start merging from the end, because if I merge this with this linked list, then it will we'll have to again merge this. So we will, if we merge this, then we will having a single linked list, then we will merge that linked list here, so we will be kind of reducing our work. So as this contain no list, so merging will be like take very less time if we have a like this list, this particular list is already made it, so we need not to do any difference here, any manipulation here. We will just need to have change some pointers here, so that like merging will take us very not merging, basically we are kind of merging, but yeah, it's not, we can say merging, we are just like here we will connect this next to here, is previous here, and like if here there are only two nodes, but there might be like say 10 nodes, so we will go through, we will have a pointer to the 10th node. We will make that node's next pointer pointing to this, and its next previous pointer pointing here. So like with this logic we will be able to merge these two lists. Then we will, after merging these two lists, we will end up with a single, like here these two lists after merging will form a single double linked list that we will merge here, and we will, like after these two particular happens, we'll return this. We already have access to this, and they will again make a merge logic here, and at the end we will return the head pointer of this particular linked list. So let's go through the code, how we will code this logic. So this is the logic. This function will be given to you. This is my extra like a layer function I am written to implement my logic. So if we are taking a copy of the head node, and we are just storing this. So we are just taking the backup of this, so that like if we directly made a call upon head, then we will lose access to our head node. So basically that's why I'm storing this in temp, and then I will return head, so that I didn't lose my, so I don't lose my control and access to my head node. So we are then I'm calling out flatten temp, flatten one, which is different function. You can see there is a one, so as, so there are different node, so it will call this function. So what this function do, this function basically checks, go through all the node, and if there is a child of a particular node, it makes this like recursive call upon flatten one, and at the end it returns the last the last node of that link, particular doubly linked list. So let's go through this code. We are again taking the copy of head node, and if head, like if these are just test checking, like if head is null, we are returning null pointer, and this backup is basically to this basically will be one step behind the current moving pointer, so that at the end of the list, because you can see this condition sets will this loop will terminate when temp reaches to the end of the linked list. So when it reaches to the linked list, we want to return the one node before that node. So that's why I'm keeping this backup node, basically to have this so every time I check this, like whether we are moving that backup pointer to the temp pointer, and then we are just uh, yeah, then we are just checking if there is child, if there exists the child, we are just making the call. And as I said, this particular function will return the last node of that list. So this is the swapping logic, this, like you can go through, and this function go through this part, and at the if the child doesn't exist, we are moving the temp pointer to the one level forward, and then at the end we are returning the backup. Backup is basically the list of the last node, and then here we are returning the head pointer. So let's submit this solution. Let's check what we get out of it. What, run the code. This time is according to like Indian time. Submitted. Let's submit this problem, although I will get all correct because I submitted this once, but for your confirmation I'm just rerunning this program. You can see we got all correct. So that's all for today. Thank you all for having patience and completing the video.